Hello out there. We're working through the 2023 AP Calculus Free Response questions. This is question number 3 for both the AB and the BC exams. I have not read the questions yet, and so I am solving these in real time. You're watching me process the problems as I get to them, so I may run into a little hiccup as I have to process something and think through it. These are not prefabricated solutions. So let's look at number 3 here. Let's see, it is a bottle of milk is taken out of a fridge. Oh, this is the milk problem. I've heard a lot of rumbling about this one. Let's see if it's as bad as you say it is. So a bottle of milk is taken out of the fridge, placed in a pan of hot water to be warmed. Ooh, sounds like we're feeding a baby. Increasing function M models the temperature of the milk. And so I like to do a little bit of game planning as I'm working. So M, that's a jacked up M. M of T is the milk temperature. They tell you that M is increasing. That means M prime of T would be greater than or equal to 0. T is the number of minutes after it is placed in the milk is placed in the pan of hot water. M is the differential equation, which normally I wouldn't take the time to rewrite this, but since I'm solving these on a separate sheet of paper, so to speak, they don't like me to do screenshots of the actual questions. I have to solve them this way. One year I did screenshots and I very quickly received an email from College Board asking me to take down my videos. So here we are. At time 0, the temperature of the milk is 5 degrees Celsius. So there's an initial temperature. Temperature at time 0 is 5. We are in units of degrees Celsius. And now, and then they also say that M is always less than 40. Okay, so there's all my game planning. And now let's start solving. A slope field is given for the differential equation. Sketch the solution through the point 0.5. Well, that is a nice question, probably only worth 1 point. And if you look at the slope field, you will see what appears to be a bunch of zero slopes. And those zero slopes right here would correspond to when M is 40, because if you plug in 40 for M, you would have a slope of 0. And then we are starting down here with a fairly positive steep slope, and we will increase towards that horizontal asymptote. So you will want something kind of like that. So that was nice. Easy question for A. Number B, use the line tangent at t equals 0 to approximate M of 2. The temperature of the milk at time 0. So linear approximation, another very nice question. Anytime you want the tangent line, you want the point, which they tell you we are looking at 0, correct? Yes, they tell you the point is 0.5. The slope will be found with the derivative, which they give us. So that would be dm dt. And pay attention to the derivative. It is a function of m. So we're going to plug in 5 for m. We are concerned when t is 0, but I'm going to plug in 5 for m. So I'll be 1/4 of 40 minus 5. And if you're really smart, you might realize that that is the same thing as 35 over 4. Now I can write my tangent line, which I usually just like to stick with x's and y's for my tangent. So like y minus 5 equals 35/4 times x minus 0. Since this is m as a function of t, I think I'm going to be consistent with the variables that they chose for the dependent and independent. And I'm going to say my tangent line is m. I really have a hard time with m's. I don't know why. M minus 5 equals my slope. So I'm going point slope form here times t minus 0. And because I'm about to use this to approximate the value of m when t is equal to 2, I'm going to change this to 35 over 4t plus 5. And then finally, we will approximate m at time 2. Yes. And that'll be approximately 35 over 4 times 2 plus 5. Let's see, that's 35 over 2. Would that be 45 over 2? Is that 45 halves? 35 halves plus 10. I think that's right. Now, what I'm doing right here is ridiculously stupid because you're not supposed to, or I shouldn't say you're not supposed to. There is no advantage to simplifying your answers. So I kind of like to just to satisfy my own curiosity, but then I'm going to draw a line through that very quickly. That way the reader will know not to grade that section. And so let's jump on to part C. I'm going to shrink this up so I can fit everything where it can all be seen. All right, let's go on to part C. And I glanced at this just a second ago. They're calling for the second derivative. I'm going to block off my pre-gaming stuff. So my second derivative. All right, so write an expression for the second derivative. So d squared m over dt squared. And for this one, I think to make this a little bit, you know what, I'm not going to do that. I was going to distribute my 1/4 because, I mean, you can. That would be what, 10 minus 1/4 m. You know what, I think I am. I'm going to distribute the 1/4. Then when I find my second derivative, I'm differentiating 10 minus 1/4 m, which will be negative 1/4. But m is not a t. We are differentiating with respect to t. Therefore, I need to multiply by dm dt. It's an implicit differentiation situation. So there's my second derivative. It says write an expression. It does say in terms of m, so I can't stop here. That is not an m, that is a dm dt. So now all we're going to do is replace dm dt with the equation that they gave us. So that's 1/4 of 40. Whoa, I have my 4 there. 40 minus m. And there is my expression for dm dt. Okay, now use the second derivative to determine whether the approximation from part B is an underestimate or an overestimate. Okay, so for part B, we did a linear approximation situation. And for linear approximation, just kind of thinking this through, if my function is concave up, the tangent line will lie below the curve near that point of tangency. If my function is concave down, if my function m is concave down, then my tangent will lie above the curve near that point of tangency. So this question on part C, to determine overestimate or underestimate, we have to determine the concavity of m, which is where the second derivative comes into play. And I think I'm going to clean this up ever so slightly to negative 1/16 of 40 minus m. And the question is that second derivative always positive or will it always be negative? And that is where this information right here comes into play. They told us a long time ago that m of t is always less than 40. So let's think about that. If m of t is always less than 40, then 40 minus m would always be something positive times negative 1/16 means that will always be positive. So I'm going to say that since m of t, not m's. Why can't I write an m? I understand my writing is weird sometimes. Since m of t is less than 40 for all t, I'm going to go back and read the how they describe that. They said m of t is less than 40 for all t. Okay, so that's what they said. So m of t is less than 40 for all t. I now know that my second derivative of m is going to be negative for all t, which makes m of t concave down. And I'm going to swap to typing because my writing is weird and it's faster to typing. And so I would follow that up by saying that since m of t is concave down, the approximation from part, E is, and your concave down, so the tangent line is above the curve. The approximation is an overestimate. Let me fix my spelling here. There we go. So there's part C. And part D is probably the solve the differential equation through separation of variables. And let me scroll down to part D here and use separation of variables, find an expression for m of t with the initial condition m of 0 is 5. So yes, very predictable, very predictable. And this is quite a nice differential equation if there is such a thing. dm dt, I'm going to rewrite the differential equation, is 1/4 of 40 minus m. And we're going to solve that through separation. So I'm going to divide by the 40 minus m, dm divided by 40 minus m. M's, what's wrong with my m's? Is 1/4 dt. There, you probably got 1 point for the separation. The antiderivatives, when you integrate both sides, you have to make sure that on that left side, the numerator is the derivative of the denominator, and it will not be until I inject a -1 in that numerator. So the antiderivative of the left side is -1 times the natural log of 40 minus m The right side is an easy antiderivative. That'd be 1/4 t plus c. Now we have to solve for m, and we have to solve for the constant. I'm going to start by moving that negative over. So the natural log of 40 minus m would be negative 1/4 t. I don't know whether c is a positive or a negative constant. And so if I multiply it by a negative, I still won't know if it's positive or negative. So I can just say plus c. AP readers don't care if you don't change the constant. Technically, I should call this C2 because it is now slightly different than the C in the previous step. But I'm going to be a little bit of a lazy mathematician here, and I'm just going to keep writing plus C. Now I'm trying to decide, should I solve for C or should I solve for M first? I have the initial condition when T is 0, M is 5. I think I'm going to solve for M. No, I'm going to go ahead and solve for, what do I want to do? Whatever. I'm going to go ahead and solve for M. So I'm going to make both sides exponents on E. And as I do this, I'm going to say that 40 minus M is AE to the negative 1/4 t. I like to bring that constant c down. You can leave the c up there in the exponent if you want. And I really just wanted to get rid of that natural log. I think I now am going to solve for a by plugging in the ordered pair 0, 5. And when I plug in 0, 5, I have 40 minus 5 is 35 equals a. E to the 0 would be 1. So a is 35. So now I can reset my solution. 40 minus m equals 35. E to the negative 1/4 t. And finally, I can wrap this up by subtracting 40, solving for m. So I'm just going to do this in one step. M is going to be 40 minus 35 e to the negative 1/4 t. So a lot of steps there. That honestly, that was not a terrible solving of a differential equation. And that is all for number 3. And we'll move on to number 4 here in just a second.